The rotary engine does have a reputation for braking, and that reputation isn't necessarily always 100% justified. There are some reasons why this is seemingly so common. We're here with Rob Dahm to talk a little bit more about rotary engine strength, reliability and tuning. So Rob, for a start, what do you see as the main reason why rotary engines traditionally have had this reputation of braking? I mean, we've all seen the memes, boost in one side, apex seals out the other side.
Yeah, so I would like to preface that by saying, because I'm not a traditional builder, I really get to see the actuality of what a typical person sees the rotary engine as. And so I've got all the variety, the 2-rotor, 3, 4, and I got the 6 in production. And so I see a lot of different misnomers or things that people think about the engine or have come from the history of the motor that incorrectly characterize it now. And so there's a lot of different things we can expand on, but I can definitely say that poor motor doesn't get it gets the reputation it shouldn't get, and it's an honor that I see a lot of people call me Rotor Daddy, when there are people like PAC Performance and others that have really set the stage for me to succeed, both with tuning or building and supporting that motor. So it's an honor to be in this spot, speaking as almost an authority or a subject matter expert, when really I'm one of the newer people to the scene, but I certainly have learned a lot and built off of the existing.
I think where you differ though from some of those shops, and obviously not to disrespect PAC or any of those who are achieving, the issue we see is obviously they're doing it commercially. There are a lot of players in the market and they want to keep their secrets,
Yes,
as they call them, to themselves, which is understandable. So they kind of don't really share too much of what's going on inside the engine. On the other hand, you're really not doing this for a living. You want to share this information so you get to see what's going on. Now, I want to really focus here on two separate elements. And I want to start, which is more my specialty, which is the tuning side of things. Yep. And I think, in my opinion, what I've seen, a lot of the rotary engine blow-ups or failures are actually the result of poor tuning, with a tuner who's perhaps had little to no experience on rotary engines and is trying to apply what they know works on a piston-style engine.
Yes.
Doesn't always work. Let's hear your take on the differences.
So I will tell you, the motion of anybody getting into tuning a rotary engine is as simple as how people perceived using E85 on a rotary engine. There was that common consensus that it was bad, that you were going to ruin the motor, and I heard of a guy or a friend that did it this way and it had problems. And so there's a lot of people that treat these engines with that sort of like anecdotal information, and so they go into tuning the engine wrong instead of looking at the facts. And I think you and I very much share that diagnostic approach and cause and effect, and see it for yourself, and having that experience, I think is what's given me a competitive advantage over many people. And of course, even as simple as just making tons of power, which is one type of challenge, but then also making that power reliably, which is the other axes of challenge.
The reliable is the key part here. So there's two separate elements. There's a lot we could dive into here, but just to keep it relatively brief, there's the fueling and the ignition timing. So let's start with the ignition timing. And the rotary engine, what's important for viewers to understand is that they're a sensitive little soul. They really need to be treated with a lot of TLC, and where we could potentially on a piston engine run the engine into light levels of detonation on the dyno. Obviously it's not preferred, but it can happen, and the engine's not instantly going to fall apart. We can find where that knock threshold is, where MBT is when we're optimizing the timing. Yeah. That's not a real good approach on a rotary engine, is it?
No. I mean, I've done that approach on a rotary engine, and I paid the price and detonated the motor. And I mean, it's the same reason I don't, and some people do, but I don't run knock sensors, because the knock is basically the moment the engine fails.
That's a really good point. I've actually had a lot of people reach out on our YouTube channel and on our forums as a result of my rotary tuning worked example, which is in one of our courses. And I specifically make the point of, I do not believe in knock control. This will be controversial. Yes. I have a lot of people here saying I'm wrong, but I do not believe in knock control, obviously for the same reason. Yep. I'll talk about that in a little bit more detail. When we're validating or tuning a knock control strategy, it's not magic. We actually need to teach it what frequencies to look for and what the noise level is, which is normal background engine operation versus knock. And the only way to do that is to make the engine purposely knock. Now, again, coming back to what I mentioned, that's not something I'm prepared to do on a rotary engine. No. Almost any level of knock can be enough in some instances to cause damage. So we want to stay away from that. All right, so that's our ignition tuning. Conservative is really the aim of the game. Fortunately, we don't necessarily see such a steep relationship between torque and ignition timing with the rotary engine, so we can kind of be a little conservative. We're not leaving bags of power on the table, are we?
No, I actually rented a hub dyno recently with my rotary Corvette and went from about 6 degrees timing all the way up to 22. And, I did see, obviously, increase in power, but it was actually so subtle. Yeah. Like I was, you're expecting 50 horsepower more, and that's not 50 horsepower more. And so I believe that, let's keep it more conservative and then just add boost. So.
Yeah, okay, so that's one element. And then the other is, as I mentioned, the fueling. And again, I think people try to apply what they know works on a piston engine. I mean, I hear crazy air fuel ratio targets being discussed with rotary engines in the low 10-1, maybe into the 9-1. I haven't found any need to run that rich, but generally I will use a little additional fuel to help with cooling. How do you approach it?
Completely agree. Now, I share all of this in my videos, but I run in Lambda, as you often do. And I found that I was running more lean than many of my friends who were saying, hey, you're going to blow your motor at that, and I have not yet. And so I run on ethanol, I run a 0.82 Lambda. And what's fascinating about that is, and we spoke briefly off camera, is that injector timing, I think, especially with large injectors, is a deal breaker on a rotary engine. And I found that myself, is that with one simple button click, my injector timing, whether it is the beginning of the time of injecting or the end, at about 50%, 30 to 50% of injector duty is extremely critical, especially when your secondaries are coming on and there's 2600s, for example, because you got ethanol and you want to really dump that in there. I found on my rotary Corvette that I was still meeting the same air to fuel ratio, but it was actually circumventing the motor and blowing by through the intake to the exhaust, igniting, and still showing the same air to fuel ratio, but it was not going through the motor, and as a result, the motor went lean.
So your actual air fuel ratio inside of the engine, which is what counts, was leaner than what you were registering. That's what you're saying?
That's correct. And so that's where I was like, okay, well, if you're tuning for a specific air fuel ratio, that's not the entire picture if you have your injector timing off.
Yeah, absolutely. I think people don't understand some of the tuning parameters that can actually affect what we're seeing. All right. We'll park the tuning side of things there. There's a bunch more we could talk about, but that's a high-level view of some of the elements that I see as problems. Let's dive into the engines now. The other thing I sort of see is that the rotary engine has always been sort of discussed as being simple in terms of it doesn't have as many moving components as a typical piston engine. Absolutely, of course, that's correct. And I think the knock-on effect of that is a lot of young enthusiasts think that, well, it's so simple. I can build it in my back shed, maybe with a bit of sand blowing in the door because you're living near the beach or something like that, and it ain't no thing. These engines still need precision when it comes to assembling them. We need to work in the same clean environment that would be building any engine. The tolerances, clearances inside them, absolutely every bit as critical as any other engine.
Incredibly critical. Now, the best place for any beginner getting into rotary engines to start is Mazda's spec, Mazda's parts, Mazda's side seals, you could even say Mazda Apex seals, but to start, using their tolerances is a phenomenal place to be. So I would go, on a budget, I would go to Amazon and get like a set of calipers, a micrometer, like all the different things to measure and make sure that your seals are in spec or the rotor is the correct width compared to your rotor housing. Like all of those things are pretty critical to prevent catastrophic failures. And after that's all verified, then yes, I think that the engine assembly is simple. But that's like the end. That's the end home stretch.
Yeah, that's the last probably 10% of the actual job. All of the hard work's already been done up to that point, correct?
Yeah, 100%. Now I do like to test, like on my 3-rotor. I purposely have non-balanced rotors. So I let the motor. I want to see, okay, what's the effect? And that motor surprisingly has worked way better than I thought. One of the rotors are dented, and so there is some level of backyard, shade tree mechanic room to give on a rotary engine, but it's only in certain areas, and you have to be aware of it.
Let's talk about what are the key upgrades that should be applied when building a performance rotary engine and maybe what order they should be. I'm guessing there's a lot of people out there who are pushing a factory engine beyond where it's probably safe, and likewise there's probably a lot of people that are building a hugely expensive long motor with parts that they don't really need for the power they're aiming for.
Yes. So I understand that a shop needs to survive by making money. That's an absolute necessity. So that puts me in a very unique position that I am not a shop. And so my job, technically, at the end of the day, I'm an entertainer. I'm not an engineer, but that's how I think of myself, is I'm engineering these things, but my job is to entertain. And so by entertaining, I love to share information. So what I've noticed is a lot of shops will add on things that, again, that are hearsay or anecdotal, but make them money to stay in business. And something as simple as lightning rotors anecdotally makes sense. Like, yes, less rotating mass for sure. But is that at 400 horsepower on a two rotor going to make a big difference? No, really. Like price per value, and especially if, say, you do have a failure in the motor, now you're having to pay all this extra money to replace a now customized part. So my job, in my mind, was to use a stock rotor, roughly the same weight as the other rotor, stock seals, and then just push that to see its limits with minimal adjustment to the motor to see when fans ask me, hey, I want to make a 400 horsepower two rotor or a 500 or 700, at what point certain modifications I feel from my experience are justified.
All right, let's talk about some of those common modifications. So stud kits, dowelling the housings to the plates. Those are sort of two of the more common modifications. Then in high-end race engines, there's clearancing of the rotors as well.
Yes.
What, if any, of those are necessary? If, let's say, we wanted to shoot for maybe 600 horsepower, nothing crazy in a two-rotor turbo.
Yeah, no, you almost nailed it perfectly from what I found, is that, starting with the idea of using ethanol to prevent a lot of carbon buildup in the motor, so you don't have that dieseling or hot spot, which I've experienced. That's one. And then two is dowelling. I'm a big fan of dowelling. Now, that was kind of shown to me. It wasn't like I discovered it. Is that when I originally purchased this motor, it was very controversial as to whether it would run well or not. But it was built with, actually, Jeff from Precision Engineering had made these 16 millimeter, which are the same diameter as the stock 2 dowels, but solid dowel bolts. So they were like a stud that was also a dowel. And my findings were that was a phenomenal solution for the torsional challenges of the motor. And so I'm a firm believer that keeping it simple, I tell fans that if they want 400 to 500 horsepower, a stud kit and then adding some dowels, which does take some machine work, but the stud kit first, maybe buy Pineapple Racing sells a solid dowel kit, which is just the upper and the lower one. And at very least the lower one alone, strengthening that side to side,
the torsional rigidity, increasing that.
Yeah, so that's the very first thing to attack, in my opinion. Especially as a street car, where sometimes you're slamming on it, sometimes you're not. It's not a purpose-built motor. That's where I attack first, and then as you go on, I have found that stock rotors, especially at high RPM, do make love to the side plates, and you'll see the scuffing and the color discoloration of the tip of the rotor, not the apex seal, not the seals, but the actual physical rotor. And I've gotten away with not catastrophically destroying my motors, but pulling them out and going, okay, you do need to take that 5/1000ths off the tip. If you're looking at the rotor spinning like this, it's the tips. You almost have to put it on a lathe and just take all the corners down, and that seems to be a good next step once you start going really high RPM.
So that's more RPM versus actual outright power,
Yes.
which you can understand essentially at higher RPM. The rotors tend to want to walk about a little bit inside of the rotor housings and just make that contact. I'm interested with that process. Is that more race only? Is there downsides in terms of increasing blow by, etc., or does it not really make a big difference?
Yeah, no. On a traditional motor, this is not a traditional motor because it has a dry sump. So there's a vacuum in the crankcase. In the vacuum crankcase situation, I don't think it makes much difference at all, because all the seals are almost being sucked to them. I can see that it wears, the more the vacuum, I have a vacuum regulator on this car, because the stronger the vacuum is, the more I was wearing down my side seals and corner seals. And so on a traditional motor where there is no vacuum holding those seals, assisting those seals, I definitely see more blow by on my 3-rotor. Like, it fills that catch can pretty quick.
Yeah, so there's compromises that we need to understand and be prepared to take. One of the other obvious questions here is apex seals And I mean, most people building a performance rotary will jump to an aftermarket Apex seal. There's literally dozens of options out there, all with their own sets of pros and cons. Then there's also the Mazda factory seals as well. My personal take is that people probably jump away from the factory seals maybe a little bit too early, and the factory seals, when tuned correctly, are pretty strong and do a great job of not beating up on the housing. So where is the sort of the line in the sand, do you think, where aftermarket seals are non-negotiable?
Yeah, so I will definitely say, and because of my adventures are very public, you'll see the old traditional rotary engine builders say that you're doing something wrong if the stock apex seals break. Now that is objectively true. You're doing something wrong, but I think that the better way to approach the motor as an enthusiast, not as a obsessive builder, but as a person that's in their garage and doing it with a reasonable budget, an aftermarket seal does have some benefits that outweigh the trade-offs associated with those benefits. And so a softer seal tends to be, which I found soft seals tend to warp under intense moments, but they never take out the entire motor. That you just lose compression, and you would said off camera that almost forces you to have to rebuild the motor before it is catastrophic.
Yeah, I mean, it's obviously never ideal when you lose compression and the engine either won't start or is really hard to start, which coincidentally is one of the big red flags with rotary engines. If it's difficult to start, chances are start looking at what's gone wrong. But of course, the failure mode there is bending and losing compression as opposed to catastrophic destruction. And when one of those apex seals lets go, there's not a lot left of your engine and also your turbocharger if it's forced induction. Look, Rob, I think we'll finish it off there. We could talk for probably another couple of hours on rotary engines, but there's a few tips, hopefully, for our viewers. If people want to follow you and see what you're up to, where are they best to do so?
Rob Dahm, ROBDAHM, on all the different platforms.
Perfect, and we'll drop a link in our description there so people can find you easy. Thanks again for your time, Rob, and enjoy the show.
Yeah, you too.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.